Fire. It's one of those things we see almost every day. It warms our homes, it cooks our food, it's been with humanity forever. But it's also this incredibly powerful, almost terrifying force of nature. So, what is the secret behind it? Well, today we're going to pull back the curtain and look at the surprisingly simple science that powers every single flicker and flame. I mean, just think about the raw, unimaginable power of fire. You see it in things like these massive forest fires, right? It can just tear through and reshape an entire landscape in what feels like the blink of an eye. Absolutely terrifying. But here's the wild part. All of that power, all that destructive potential, it all comes from something so small. It starts with a single, tiny, controlled reaction. Just one little spark that unlocks this massive cascade of energy. Which really brings us to the big question for today's explainer. What is actually happening on a chemical level when something burns? What is the secret science of fire? So, where do we even begin? Well, to really get a handle on fire, we have to pop the hood and look at its engine. And that engine is a chemical reaction called combustion. At its absolute core, combustion is really just a chemical process. You take a substance, we call that the fuel, and it reacts super fast with an oxidizer, which is usually just the oxygen in the air around us. And when that happens, boom, it gives off heat and light. That's it. It's a fundamental way of releasing stored energy. Now, this is what I find so cool. This slide really shows you the two different personalities of combustion. On one side, you've got this crazy, intense, brilliant light from a burning magnesium ribbon. And on the other, the gentle, steady flame of a candle. They look completely different, right? But believe it or not, it is the exact same chemical process making both of them happen. Okay, so what's the recipe for fire? How do you make it happen? Well, it all boils down to this really simple but super powerful idea, the fire triangle. This is basically the blueprint for every single fire, from a tiny match to a raging inferno. So the triangle has 3 sides, and you absolutely need all 3 for a fire to get started and to keep on burning. What are they? Fuel, air, and specifically the oxygen in the air, and heat. If you take away even one of those sides, the whole thing just collapses. The fire is gone. Let's start with the first one, fuel. This is pretty straightforward. It's just anything that can burn. It could be a solid, like the wood in your campfire, a liquid, like the kerosene in an old lamp, or a gas, like the LPG that fuels your stove. It's basically the food that the fire eats. And this is a perfect illustration of that second side of the triangle, air. It's a classic experiment. You can see the candle burns just fine when it's got plenty of air. But the moment you start to restrict that airflow, the flame starts to sputter and you get smoke. Cut off the air supply completely and it's out. It's that simple. No oxygen, no fire. All right, the final piece of our puzzle is heat. But here's the catch. It's not just any heat. Every single fuel has a specific temperature it needs to hit before it will burst into flame. We call this its ignition temperature. Think of it like a secret password the fuel needs before it can start burning. This brings us to a fantastic little experiment you can actually try at home. Carefully, of course. If you hold an empty paper cup over a flame, poof, it catches fire almost instantly. But if you fill that same kind of paper cup with water, you can hold it right over the flame and nothing. It won't burn. So what's going on here? The answer is all about that ignition temperature we just talked about. See, water is amazing at absorbing heat. It's literally acting like a heat sink, pulling all that energy from the flame into itself. It keeps the paper from ever getting hot enough to hit its ignition point. Pretty clever, right? And now for the really practical part. Understanding this fire triangle isn't just a neat science trick. It is the absolute key to controlling fire, to taming the flame. So, how do we do it? Well, every single method we have for fighting a fire is designed to do one thing: break the fire triangle. The whole job of a fire extinguisher is to remove one of those 3 essential sides. So, you end up with 2 main strategies: cooling and smothering. When firefighters are spraying a massive amount of water on a fire, they're cooling it down. They're removing the heat side of the triangle. And when you throw a fire blanket over a pan fire in the kitchen, you're smothering it. You're getting rid of the air side. This is exactly why we have different kinds of fire extinguishers, and you have to know which one to use. You can never use water on an electrical fire. That's a huge shock hazard. Instead, you'd use something like this CO2 extinguisher. It shoots out a cloud of carbon dioxide that's heavier than air, and it just sinks down and smothers the flames, creating a blanket that cuts off the oxygen. Okay, so we've covered the reaction and how to stop it, but now let's zoom in on the part we actually see. What even is a flame? Ever wonder why a candle burns with a flame but a piece of charcoal just glows? Well, the secret ingredient is vapor. The flame you see is actually burning gas. With a candle, the heat melts the wax, it gets drawn up the wick, and it turns into a vapor. It's that vapor that's on fire. Charcoal, on the other hand, doesn't really vaporize, it just burns as a solid, so you get that red-hot glow instead of a flame. And if you look really closely at a simple candle flame, you'll see it's not just one thing. It's actually made of 3 different zones. You've got that dark inner zone, right near the wick. That's just unburnt wax vapor. Then you have the bright yellow middle part, where there's some combustion going on. And that faint, almost invisible bluish layer on the outside, that's where the real action is. Now, this isn't just trivia. People use this knowledge. Goldsmiths, for example, need super high temperatures to work with gold and silver. And what do? They use a blowpipe to aim that faint outermost part of the flame right at the metal. Why? Because that's where complete combustion is happening, and that makes it by far the hottest part of the flame. Okay, for our last section, let's zoom all the way back out. Our entire modern world is basically built on combustion, from our cars to our power plants. But not all fuels are the same, and burning them definitely comes with a cost. So how do we measure how much bang for your buck you get from a fuel? We use something called its calorific value. And as you can see from this chart, the differences are huge. LPG packs almost 3 times the energy of wood, kilogram for kilogram, and then you have hydrogen, which is just in a totally different league. But of course, releasing all that energy has a downside. There are hidden costs. When you burn fuels like wood and coal, you can get nasty byproducts like soot and poisonous carbon monoxide. Even when combustion is perfect, you get carbon dioxide, which is a major driver of global warming. And some fuels, like diesel and coal, release oxides that lead to acid rain. And that really leaves us with one last big question to think about. We've seen that the science behind fire is actually pretty simple, right? It's just a little chemical triangle. So why is managing that simple reaction on a global scale, harnessing its incredible power while dealing with its harmful consequences, one of the most complicated challenges we've ever faced?